I'm sorry. This is again. No, this is not me.
Anyway, we're delighted to
Well, good morning. It's a pleasure to be here. We'll decide in the end whether the talk was very interesting or not. In any case, it's a pleasure to be in Cortona. It's a pleasure to be in a live conference, and also a bit challenging to give talks live again. So let us see. What we're talking about today is about two components, which is something related to complex dynamics, which is not the main theme of the conference. So our first goal will be to make sense of this title. So we will first try to understand what it is what we're talking about when we talk about invariant escaping the two components. And then I will tell you something to put this into context. I will tell you some results of what is known in complex dynamics in one variable and complex dynamics in two variables concerning these escaping from two components. And finally, I will tell you about some new results which were obtained with a variety of friends and co-authors, Arozio, Fornes, Peter on one hand, and Sarah Quenzed on the other. Let us start with complex dynamics. So what is complex dynamics? You take a manifold, let's call it M, and you want it to be an analytic manifold, a complex manifold, and you consider a function which needs to be holomorphic to respect the structure of the manifold, which acts on this manifold. So it's a function which goes from the manifold into itself, and what you consider is the nth iterate of this function. So you apply fn times, and you basically want to understand what happens to points when n goes to infinity, okay? So if you look at it from the perspective of a single point on x on your manifold M, you apply f, you go somewhere, you apply f again, you go somewhere else. You kind of want to see what happens when you apply f infinity many times. This is the very first basic level, and what you can points do? They can converge to the boundary, go around and come back to themselves, go close to the boundary, come back, close to the boundary, come back. They can do a variety of behavior. The second thing that you want to look at is, so now you kind of understand what a single point does. So what's the relation? Does this point behave similarly as its neighbor, or does it do something and his neighbors do something else? And finally, once you kind of understand how the orbit of points relate to each other, you want to split your manifold M into sets on which points kind of do the same on the entire set. And once you have this set, you want to study its properties. And its properties can be studied from many points of view. For example, you can study its topological properties, its geometric properties, its Hausdorff dimension. You can study many different things about this set. So this is the general goal of things that you study at first level when you look at complex dynamics. And then you can go up and study spaces, parameter spaces of functions in which you let your functions vary. But this is not what we will do today. Today we will stick with one specific function. So the very first dichotomy that you encounter when you look at the dynamics of points is to look at points which go to the boundary of your manifold and points which stay inside the manifold, which doesn't mean that their orbit is bounded, okay? So you have points whose orbits converge to the boundary, points whose orbits stay in compact sets. The orbit is the union of your points together with all its forward images, okay? So the orbit of a point x is x union f of x, union f squared of x, f cubed. Well, you know how to go on. So the very first dichotomy is about points which converge to the boundary and points which do not converge to the boundary. And here there is something to be careful about, is that you may converge to the boundary, you may stay in a compact set, or you may go as close as you want to the boundary, then come back and go back and forth. Sometimes we call them informally bouncing points. So I don't know why this is going along anyway. So one of our main definitions for today is to say that a point is escaping if its orbit converges to the boundary. Okay, so now we're making sense of the word escaping in the part. And if you're not converging to the boundary, we say that the point is non-escaping. So this includes the case of points which stay in a compact set and points which go back and forth. Let us look at two very simple examples. One is we will be concerned with our manifold M will be C or C2 for today. Nothing more exotic than that. So let us look at one example of iteration in C and one example of iteration in C2. In C, just consider the function z squared, okay? What does the function z squared do? You take your unit circle. If you are in the unit circle, when you square your number, you will stay in the unit circle forever. So you're not escaping. If you are inside the unit disk, what will happen? Your points will slowly converge or fast, depending on your case. Will slowly or fast converge to 0, because if you square a point with modulus less than 1, your modulus will become smaller and smaller. And if you are outside of the unit disk, well, what will happen that your modulus will become larger and larger, and so you will spiral towards infinity. This example is quite simple. It's one of the basic examples in one-dimensional complex dynamics. The next example is an example in C2. Okay, so now our manifold M is C2, and we look at this linear function, innocent linear function. F of zw is equal to 2wz. So what do? You swap the coordinates and you expand the second coordinate, which now becomes the first one, by a factor 2. What is happening here? Well, clearly 0 stays the same. Okay, f of 0, you can apply f as many times as you want, and you will stay in 0. But any other point, one coordinate at a time, will move towards infinity. So, technical detail for today's talk, this is a debatable stuff, but this is a debatable thing, but we will not debate it today. For today, we will consider the compactification of C2 as the complex projective space. Okay? There are many ways to compactify C2. One that seems particularly relevant for dynamics is to consider the compactification with adding a line at infinity and considering this to be the boundary of your C2. This gives you the complex projective space. We have seen it yesterday in one of the talks. And we call L infinity design infinity. So unless you are the origin, any other point under iteration converges to the boundary. So everybody is escaping except for the origin. Now, the second basic, so first dichotomy, you go to the boundary or you don't go to the boundary. Now, second dichotomy is what I was telling you in the very first slide. There are points which move together with their neighbors and points which go on their own. So this needs a proper specific mathematical definition. We talk about stable sets are the points which basically move together with the neighborhood of them, and unstable points, the unstable set is a set of points which essentially behave differently from points in their neighborhood. The specific mathematical definition is the following. We say that a family of holomorphic function is normal. Many of you probably know this definition from before. If every sequence has a subsequence which converges uniformly on compact subsets to a holomorphic function. The holomorphic function depends on the compactification, okay? Holomorphic functions, the holomorphic function depends on which compactification you choose. So in our case, we look for holomorphic functions which will go from a neighborhood of your point to your P2 if you are in C2, or to C hat, the Riemann sphere if we are in C. Let me go over this again, just one more time. We take a point, we take a neighborhood of it, and we look what happens to this neighborhood under iteration, okay? The family of iterates M is a family defined on this neighborhood. So now we look at whether this is pre-compact in the family of all holomorphic functions which go from our small neighborhood to the closure of the manifold. If it's pre-compact, so basically every sequence is a convergent subsequence, it kind of tells you that all points behave the same asymptotically, and the same behavior is this limiting function. And the stable set, so the definition of points behaving approximately the same as the neighborhood of them, is exactly in terms of the definition of normality. So the stable set, which is usually called the 2 set in our setting, is the set of points which have a neighborhood U on which the iterates form a normal family. Now, let us go back to our examples. In our examples, we said in the first example where we have z squared on the complex plane, what did we say? We say, well, the unit circle goes to itself. The outside moves to infinity, and the inside moves to 0. So we said that the escaping set is the complement of the closed unit disk, and the non-escaping set is the closed unit disk. What about if you look at it in terms of stable set? So if you are outside, any little neighborhood outside will go towards infinity. So our limit function will be infinity. We don't even need to go to subsequence. If we are inside, a small neighborhood of any point in the inside of the disk will converge to 0. Again, no need for subsequences, okay? We need the subsequences for the general theory, but in this specific example, there's no need for subsequences. And what happens if you are in the unit disk? Well, in the unit disk, when you square a number, you're essentially doing a period doubling. And if you take a neighborhood at any point on this unit circle, you have a little bit, the blue one, which converges to 0, and a little bit, the yellow one, which converges to infinity. So there is no way you're going to have a limit function which is even continuous. Forget about holomorphic. So let me try to change this because I don't like the fact that it goes by itself. I'm just going to try to stop this. I will try this. This is worse. Sorry, it usually doesn't decide on itself when it's time to change slide. So serious. Okay, let us try again. Okay. So we were back to our example in C2. Now let us look at our example in C2. Again, our linear function, the one that we had before, we swap and we multiply the new first coordinate by a factor of 2. So we said that everybody except the origin converges to infinity. It's a typo, should be a big F. Oh no, this is a good thing. So now here we have subsequences, okay? Look at what happens. If I take the even iterate of my function f, this is just, I multiplied both coordinates by 2 to the n. If I take even iterates, because in the first time I swap and I multiply just the first one by 2, then I swap again, this one remains multiplied by 2, and this one also gets a 2. I applied it 2n times, and my function f to the 2n is just 2nz and 2nw, okay? So basically, I just multiplied both coordinates by a factor 2 to the n. And this converges, if you're familiar with the projective notation, this converges to the point z w0, which is some point here in the line in which the coordinates here are the ratio between the initial point z and the initial point w. So notice that so this function, if I take the limit, now we will take the limits later, but if you look at it, so if you look at it, this is a function which will squeeze all of your complex, all of your C2 minus the origin towards the line of infinity, and the image will be open. Okay, so your limit function will be a function whose image is in this line of infinity, because we always converge to a boundary. As we said, they are all escaping points. What happens if you take the odd iterate? Something very similar. Okay, there's also a typo here. So what happens is that you will have a 2 to the n plus 1 here and a 2 to the n here. So you will converge to the point 2w over z in the project 2w z 0 in the. No, there is no typo, it's actually correct. So you already took the limit. So in this case, I have two distinct limit functions, one for the even iterate and one for the odd iterate. What is the only thing that I want to point? What is the main thing that I want to point out with this example? Everybody is escaping. Everybody except the origins in the Fatou set. So, but you have two distinct limit functions, both of which squeeze the entire space on the complex line of infinity. Other questions about it, because it's a bit of a different topic from the usual ones. Do the examples make sense?
So here,
yes.
Is there a difference if you consider the one-point compactification or C2 or
So in going to the boundary, no. In definition of the escaping set, no, because you go to the boundary. But in the definition of a two set, it's not even clear if it doesn't make sense to consider holomorphic functions to the one-point compactification of C2 because it's not a holomorphic manifold. Right? Yes. The definition changes. We have an example of this. Well, we have examples to say that well, one of the two sets could be larger. I don't remember which one. I need to think about it, but they are different in principle. You can find examples in which essentially they are different. So this is the compactification is crucial here, and we may debate a long time on what is the correct compactification. For sure, I think we want a complex manifold. But now, okay, historical note. Until now, most complex dynamics in C2 and higher was done with polynomial automorphisms. And essentially, modulo a few theorems on the way, you can see that if you have polynomial automorphism, there is basically one way to go to infinity. And so somehow, in this case, whether you study the Fatou set in which you take the one-point compactification, you say, if you go to infinity, no matter how you are normal, and well, whichever compact set you deal with it, it's basically no difference. The difference really comes out when you start studying things which are not polynomial. And at that point, this seems at the moment to be the right compactification to take, but I'm open to discussions, okay? So when you study polynomial automorphisms, you don't care. When you start studying stuff which is non-polynomial, then it does make a difference. So we are ready to understand the title. So what is an escaping invariant Fatou component? An escaping invariant Fatou component is a connected component of this stable set, this Fatou set, which is invariant, which is a complicated word to say that f of your Fatou component is contained in your Fatou component, and the points are escaping. Okay, so you have your Fatou component, which is a connected component of the stable set. It maps inside itself under your function, but while mapping inside itself, everybody moves towards the boundary of the Fatou component, and more specifically, the boundary of the Fatou component, which is contained in this line at infinity, which is our boundary of this space. And this is a very nice classification of invariant Fatou component, okay? Beyond the so escaping Fatou components are a special case of all components of the stable set which map into themselves. And classification of Fatou components which are invariant, not necessarily escaping, is a very classical subject in one-dimensional dynamics and still needs work when you look at the C2 case. So essentially, let us now, I would like, before talking more detail about the escaping Fatou component, let us go over what are the cases which are known for general invariant Fatou component, so that we try to understand what we are supposed to expect in the escaping case. What are the examples that we will keep in mind? There are many more, but we will look at polynomials in C. Many of you may have seen the Mandelbrot set or have heard some talk at some point about the iteration of the polynomials. Then we will look at what happens for transcendental entire functions. So a function which is entire, holomorphic on all of C, and which has an essential singularity at infinity. And we will draw a parallel between what happens in one variable and what happens when you go to C2. So what kind of maps do you study when you look at dynamics in C2? There is still so much to study, even about automorphism of C2, that I think most of the dynamics in C2 in the past 20 years has been concentrating on studying automorphism, not necessarily general maps from C2 to C2, but automorphism. Notice that, well, we'll talk about philosophy later, but we will consider two different cases of automorphisms of C2. Polynomial automorphisms of C2, and you can reduce to a special case of automorphism, which is called polynomial Henon maps, and transcendental automorphisms of C2, and we will reduce to a special case, which are called transcendental Henon maps. Again, here there is a little bit of something to be careful about, because what a polynomial automorphism is makes sense. When we talk about transcendental automorphism, maybe it would be more correct to talk about non-polynomial automorphism. Because when you look in C, as soon as you're entire and not a polynomial, as soon as you really become a transcendental function, you have infinity, you have Picard's theorem, which tells you exactly how you behave near the essential singularity, etc., etc. So somehow, the class of non-polynomial entire function from C to C is kind of uniform in its own way, while the class of non-polynomial automorphisms of C2 is very vast, and they can exhibit very different dynamical behaviors. Anyway, these are the four classes that we will talk about, and we may debate about the term transcendental, another things to debate about. And let us start with the classification of the two components for polynomials in C. This is let's say, an ancient work. It goes back to the 20s, and mostly to Fatou and Julian, which were the two French mathematicians which kind of started complex dynamics a long time ago. So let us look first at the escaping Fatou component. Let us look for 1 second at this formula, okay? When you have a polynomial, there is leading coefficient AB with the leading term z to the d, and then you have lower order terms. So when you go near infinity, really, the only thing that matters is this leading term, a, b, z to the d. Basic like estimates. Which means that essentially, near infinity, in a neighborhood of infinity, which will be more or less round, your max is really expanding like z to the d, exactly like our basic example in the very second slide, in which we had z squared. Here we have z to the d. Now, so what happens is that in a neighborhood of infinity, you converge to infinity. Your iterates converge to infinity. So in the neighborhood of infinity, there is a neighborhood of infinity which is contained in the stable set. And in this stable set, the dynamics will be that the iterates at every point converge to infinity. And this is called the attracting basin of infinity. It's the only possible escaping Fatou component that you can have, invariant escaping Fatou component that you can have. Why? Because as soon as you jump into this neighborhood, you're going to be attracted to infinity. So no other behavior near infinity is possible. And if you want, you can consider this as the fact that a polynomial you can really see at the map from the Riemann sphere into itself, in which infinity is a fixed point. And you can compute its derivative. The derivative has modulus less than 1. So it's really like a fixed point that you can imagine attracts everybody in a neighborhood. What happens to non-escaping Fatou component? Then you basically have three possibilities. I'm going to go over it quickly, and then we're going to see the picture, and everything will become more clear. So you can have an attracting basin, which means everything converges to a fixed point inside. A parabolic basin, which means that everything converges to a fixed point in the boundary. And a rotation domain. They're called Siegel disk in complex dynamics. It essentially means that you're conjugate. You have a domain, which is essentially a disk, and your dynamics may be more or less complicated because your function is non-linear, but you find a change of coordinates, holomorphic, whatever that is, and in that change of coordinates, you get a disk, and your points are rotating. But via this change of coordinates, you will kind of see the dynamics of the rotation of the disk on your rotation domain, on your Siegel disk. Before we go to the picture, let me point out something. So when we look at Fatou components, there are essentially 2 points of view that you want to consider. One is, what is the dynamics in this component? So how do points behave? And you kind of want to look for some good coordinates in which your function essentially behaves like ideally some linear map, if not some map which is canonical in the sense that it is as simple as possible. So this is kind of a dynamical classification. And you have a different point of view in which you want to look at the geometry of these sets or the topology of these sets. So what happens in the polynomial case is that when you look at your neighborhood of infinity, you have a very special normal form. Your function up to a change of coordinate is really the function of z to the d, which is basically the one we saw in the very first example. And the topology of your attracting basin, of your unique possibly existing Fatou component, escaping Fatou component, is that it's either a disk or, slightly cheating, a disk minus a Cantor set. Okay, not completely true, but essentially true. For quadratic polynomial, this is true. They're either a disk topologically or a disk minus this Cantor set. And in one dimension, as we all know, essentially the topology is very strictly connected with the geometry. So if you're a disk, you are up to be a holomorphism in the unit disk. So in some sense, in one variable, understanding the topology of this two component gives you a lot of information about their geometry. Now, what happens to the other component? Well, they are all disks, they're all simply connected, and for each one of these cases, you have a good normal form, a good model function to which you are equivalent up to a change of coordinates. Let us clarify this with a picture. So, an attracting base, you should really imagine it as a disk, which everybody goes to some points, which I drew in the center, but of course it's not a true disk, so it's somewhere in this basin. A parabolic basin is a disk in which everything converges to the boundary, not generically to the boundary, one specific point in the boundary, okay? And a rotation domain is a domain in which points move in closed orbit, which you can think of as Jar-Jar curves. And so there is kind of a center whose orbit is itself, a fixed point we call it, and all other points are kind of rotating around this point. Let us keep this in mind because you see, a priori, there could be many more possibilities for the limit function. You could converge to some set on the boundary which is not a point, or other things. But the fact that you converge, by definition of normality, you converge, your limit functions are holomorphic, by definition of normality, make it so that they are either open or constant. We are in one variable, okay? So there is not much room for creativity. Either you converge to a point, or you converge to a function which is open. In the first case, you converge to a point. Second case, you converge to a point. Third case, converge to a function that is open. Actually, you have infinitely many limit functions. You can do your math, but it's kind of believable that you keep rotating, clearly open sets, keep moving to open sets, and it's volume preserving. Now, let me tell you a word about the proof. So the very first step is to check that your two components are simply connected. And this is basically done by the maximum principle. You can look at your definition of normality. You can look at it in terms of the derivatives of this iterate staying bounded. Well, use the maximum principle, you see that there are no holes. At this point, once you see that they're disks, we are in one variable. So topological disks are basically the straight unit disk. In the straight unit disk, you have this powerful theorem, which is called the Gromov theorem, which tells you that any map from the unit disk into itself has some point, which is called the Gromov point, to which everybody converges to. This point can be in the center, in which case we are in the attracting basin case, or it can be on the boundary, in which case we are in the parabolic basin case. So, well, the Gromov point says, unless you are a rotation, you have this fixed point which attracts everybody. So either you are a rotation or you have this Gromov fixed point, which is either on the boundary or in the center. Now, let me show you some pictures. This is, so the black one is the attracting basin of infinity. This is the quadratic polynomial. Well, this is the quadratic polynomial from z squared plus c. And you can see that these snowflakes are like, you can see that these snowflakes really form a counter-set structure. So your attracting basin of infinity, your unique, possibly existing, escaping through two component is a disk minus the counter-set formed by these targets. In this example, this is a parabolic basin. The parabolic point will be here, and points will move towards these parabolic points following some very peculiar dynamics, which is called, well, some very peculiar dynamics. This is another image of quadratic polynomials. The outside of this beautiful picture is a tracking basin of infinity that if you look at it in the Riemann sphere, it's a disk. And each one of these is a two component, each one of these blocks. One of them, it could be this or this, it depends, because they are symmetric anyway. Say this one is invariant, and you will have points which rotate around some center. And this one is a case of an attracting for two component, but for aesthetical purposes, it's not invariant. It is really a cycle of components. This big one maps to the small one, which maps to the middle one, which goes back. And you really have limit functions which converge to 3 points in the middle of these components. So, what happens for transcendental functions? For transcendental functions, the only true difference is that now infinity is an essential singularity. So all of a sudden, you cannot have that the neighborhood of infinity is mapped into itself and everybody in the inside converts to infinity. All of a sudden, Picard's theorem tells you that no matter how small neighborhood infinity of you take, it maps over the entire complex plane, possibly minus one exceptional point. So really, interesting dynamics sneaks in all the way to infinity, and a whole new possibilities, whole new range of possibility opens up for escaping for two components. And these escaping for two components are called Baker domains. You can define Baker domains in many ways. Our definition for today is that it's an escaping invariant for two components, which is not an attracting basin of infinity. Okay, so all cases except the one for polynomials. Basically, any escaping for two components that appears for transcendental function is called the Baker domain. And there is a nice classification of these Baker domains in one variable, which is slightly different from what you would expect. So if you look at it very naively, you remember the parabolic case? We said we have a point in the boundary that everything converges to this point in the boundary. At a very naive level, you may think that Baker domains are just parabolic basins on which the parabolic point is moved towards infinity. This is not the case. In fact, there are different dynamical behaviors that can occur on these Baker domains beyond the one for parabolic. And again, let me go over this quickly, and then we look at the picture, and hopefully the image will be more clear. So you can have something which are called hyperbolic Baker domains. Again, Baker domains are also connected. We say that they are biolomorphic to the right half plane because the normal forms of the maps are simple to write on the right half plane, but really, we all know that the half plane and the disk are the same in one variable, okay? They are biolomorphic. So really, all these Baker domains like this, and you have three possible dynamical behaviors. One, which tells you that your function is essentially an expansion. If you want, this is kind of what we were doing with our model function in situ. Morally, you were expanding both coordinates. So in one variable, this is called hyperbolic behavior. Essentially, you multiply your coordinate z by a constant, which is say real, which is not necessary, and with modulus strictly bigger than 1. So you move towards infinity in this specific way, or you can be essentially a parabolic domain. You don't want to get into this too much, now we will see the picture, or you can be something which is slightly different from parabolic domain. Let me show you the pictures and comment on it in a minute before we move to C2. Now, you should imagine that up to a biolomorphism, again, I'm slightly cheating here as well, but I don't want to go into this, but you can imagine you have some component in your true C, okay, so where your true function is acting. Everybody moves towards infinity. Up to a change of coordinate, you can imagine these three scenarios. Scenario one, your for two component, which is simply connected, is the right plane, and you translate parallel to the boundary. The arrow is this way, but it could be the other way as well. It doesn't matter, you can have both. Other case, your for two component, up to the holomorphism, is a right plane, and you move transversely to the boundary. Last scenario, your for two component, again, is essentially the half plane, and it's like you had a source from which everything was coming and converged to infinity from there. The classification of non-escaping invariant for two components for transcendental maps is exactly the same that was for polynomial. So the new entry, when you look at transcendental maps and invariant escaping for two components, are these Baker domains. This is exactly the same theorems we had before, just translated for transcendental maps. And these are a couple of pictures of what happens to attracting basins, and this is a rotation domain for transcendental maps. Here you see these are the curves on which the orbits are moving. This is a Baker domain in which everything moves to the left. So this is really also your biholomorphism in this case will be tangent to the identity when you go towards the left, very close to minus infinity, let's say. And well, notice something that in the other, some very silly detail, okay? In the other picture for polynomials, all the drawings were in a compact part of the plane because somehow the non-stable dynamics, the interesting dynamics was happening in a compact set. As soon as you look at transcendental maps, the interesting part of the picture is moving all the way towards infinity. All of a sudden, you have these decorations which become unbounded, and the dynamics is really interesting to study, no longer in a compact set, but you really need to consider your entire C. Okay, doubts about one variable before we move on one step? Okay, let us start by looking at which maps are we considering in C2. Okay, in C, it's either polynomial or entire transcendental. In C2, we restrict to automorphism, and we restrict to specific classes of automorphism, which are in a sense very small, because well, they are maps in this form. Either polynomial or let's call them transcendental for today. They are an interesting iteration in the first variable, which could be a polynomial or a transcendental entire function, and a linear perturbation in the other coordinate. And then a swap. Kind of remind us of our linear example in the very beginning. These are the two classes that we are looking at now. We are restricting to these two classes because they are basically kind of some of the most studied cases in several complex variables. And I will say something more about some examples that we have for other classes of automorphisms. Why these maps? One important motivation for polynomial maps is that you can show that in some sense, this is also theorem, and then you deduce that in some sense, all the non-trivial dynamics that you can have when you look at polynomial automorphism is due to finite compositions of these polynomial Henon maps. So you study them and you feel like you understood anything that can happen for polynomial automorphisms. Transcendental maps do not have this nice property. Again, I'm not an expert in this, but the class of non-polynomial automorphism is really huge. So somehow it's not expectable that you can have a small class like these maps, which are the very special form, or even finite composition, to capture the whole possible dynamical behaviors that you could have. But there is a great advantage that it's an interesting class to study because there are many new phenomena which appear with respect to polynomial maps in C2 and with respect to transcendental maps in one variable. So they really exhibit new dynamical features, and yet you can use tools to study them, which come from two different worlds. The worlds of polynomial Henon maps, in which we have hundreds of papers, and the world of transcendental maps in one variable, which also is a well-developed field. So we have a little bit more of an intricate definition of what is an escaping Fatou component in C2. So you remember, if a Fatou component in one variable, either you were going to infinity and you were escaping, or by the classification, all your orbits were staying in a bounded set. Now, when you look at Fatou components in C2, you need to be this dichotomy between going to the boundary or staying inside is a bit more delicate. So the definition is that an invariant Fatou component is recurrent if some point accumulates in the inside of the component. A priori, you may have some points which accumulate inside and some points which go to the boundary. A posteriori, after you classify the Fatou components, you understand that this is not possible. Either all orbits accumulate inside or orbits accumulate in the boundary of the component. For now, it's not escaping, okay? We're just talking about Fatou component. So eventually, you can see that there is a dichotomy here. You have your Fatou component either for these two classes of maps, okay? Standing assumption, we are talking about these two classes of maps. Now, there are really two possibilities. Either all limit functions stay inside, or all limit functions converge to a boundary. And of course, our escaping Fatou components are the ones in which you converge to the boundary, not only, but also to the line at infinity. So it's a special case of non-recurrent Fatou components. Should I repeat this last part? Fatou component. You prove by classifying them, it's not obvious from the definition, that either all iterates converge to the boundary, or iterates stay inside. If they converge to a boundary, And moreover, they converge to a part of the boundary of your component, which is on the line of infinity, you call them escaping. And so a limit function is just, you remember when we defined normal families, we said a family is normal if every sequence of iterates has a convergent subsequence. Now, all these limits are called limit functions. Why am I going, let me go over the definition, then I will explain by hand waving. So we say that a limit function is one of these functions that you get when you take limits of iterates. So when there exists a sequence of iterates which converges to this holomorphic function, to the closure of your manifold on compact subsets. And once you have a limit function, you can look at the rank of this limit function by looking at the rank of its differential. And then you can use differential geometry to say that the image under this limit function has generic dimension, which is exactly the rank of your function. Yes, and then yes, so this is by definition, because if you have a Fatou component, means that at least some subsequence of the iterates converges to some holomorphic functions, and you could have many. Now look at this limit function. You have your Fatou component. What does this limit function do? It takes your Fatou component and either it squeezes to the boundary, so the image of the Fatou component will be something in the boundary, or it will be something in the inside. Yeah, it could be squeezed half in the boundary, half in the inside. No, it cannot. Okay, you can prove it. And now let us look at the possibilities quickly, hand waving, then we will read it in the slides. Now you have your Fatou component. We are in dimension 2 now. So when you have a holomorphic function in dimension 2, the rank of this function may be 0, it's a constant, 1. The image is manifold of dimension 1. Rank 2, it's an open map. So essentially you have this possibility. Your Fatou component may be mapped into the boundary, which has morally real dimension 3. This is not true, but morally it's a fractal, but morally it's a real dimension 2. So if you go to the boundary, your image of this Fatou component is either some manifold, modulo, irregular points, blah, 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 of dimension 1, or it's a point. Okay? If you map inside, it could be a point, could be some manifold, dimension 1, or it could be some open set. And if it's an open set, you can show it the entire component. Now, if you want to look at it from this point of view, when we were looking at Fatou components in C, an attractive basin is recurrent because the limit functions go inside, and rank 0. Parabolic basins are non-recurrent, rank 0. Rotation domains are recurrent, rank 1. Nothing else is possible in one variable. And Baker domains are all non-recurrent because they converge to the boundary of rank 0. The technical issues, so my computer is supposed to be plugged in. What is it now? This is supposed to be. No, okay, molto in fretta una volta che avvisa. My computer is 7-year-old. And so, yes, it's working. So once it warns, it's going out of battery, means if you don't hurry up, I'm gonna die now. Okay, we survived. My computer did not die. So we can move on. Do not read. Oops, è sparito lo schermo. L'altro schermo. Okay, do you want me to finish like this? Because we only have 10 minutes left anyway. Okay, so how does the story go on? You classify your, let me finish like this. Okay, wait, 5-10 minutes, we chat informally. We have 15 people. Okay, so how does this go on? You have, now you look at what happens in C2, and you get a decent classification of recurrent Fatou component. So basically, they are kind of the upgraded versions of what you get in one level. You get an specification for the current one, but it's still very unclear what happens when you have non-recursive components. So it's very unclear what happens if your limit function goes to the boundary. And what is the main of the request? The main of the request is that you have two components. It's non-recurrent, so everything goes to the boundary. Can you have limit functions for any one? So can you have, if you have two components, instead of being mapped to a single point, really maps to a one-dimensional manifold in the boundary? It's not known. There are no examples known. Okay, let me go over this sketch of a two components, recurrent for two components for polynomial genome. This is the picture of what I just told you, that the classification is very well understood for recurrent for two components, for basically both polynomial and transcendental polynomial. You could converge to a point on the inside of your component. You could be squeezed to a surface on which you act as a rotation. You could have something which is not well understood, but essentially your limit functions are of rank 2. And then in the polynomial case, there is one single possibility for the escaping of the component, which is morally the attracting basis that you have in one level. More complicated structure, it's called the solenoid structure, we don't care. But morally, it's again an attracting basis. Because somehow, when you have this map, you may not remember the, oh, look, here we have it. When you look at this specific expression of the map, you can see that it's really, when you go to infinity, really the leading term is the polynomial factor Z, and everything behaves more or less in one variable. Now, what I was trying to tell you is that there are no known examples of non-recurrent components of rank 1, in which everything squeezes on a manifold in the boundary. And it's a big question, well, a big question to me. It's a question which is generically asked where they can exist. You don't want to read this theorem, but there are some cases in which you can exclude them. So they may exist or not, but you at least need some assumptions. Under some assumption, you can rule them out. And for general non-polynomial automorphisms, there is not much you can say, but in this case, you can find examples of these non-recurrent two components of rank 1, and some so the first examples were given by Jupiter and Venus, and then we have new examples by Bocchara, Braccia, and Jupiter. And what are the features of these examples? So now the question was, can we have rank 1 limit function from the boundary of the two components for monomats, transcendental polynomials? Answer, we don't know, but we know that if you look at general automorphisms, no assumption on the form, they are not constant Jacobian like the genome examples, but in this case, we can find them. What is interesting is that they're dynamically very similar, all these examples. So essentially, they are C2, well, you can construct C2 or like C times C star. We're looking at the dimension 2, you can go up dimension. And they are morally parabolic. So the idea is that you kind of move in a parabolic way towards this limit surface on the boundary, which is the coupling. These are the examples that we know for non-recurrent for the components for more general classes of automorphisms than the one that we are considering. And what happens when you now go to escaping components? So all our talk was supposed to go, this is basically the last slide. So give me just 1 minute and I will be done. So what is happening when you drop, when you allow the limit functions to go not to a fine part of the boundary of your two component, but to go to the part of the boundary which is at infinity. So in that case, you can actually construct these rank 1 limit functions with explicit examples, which are transcendental perturbations of the very basic examples that I gave you in the first slide. So if you look at functions of this form, this form, then I will go up to the other example. If you look at examples of this form, which are essentially our linear map from before, you see this is the linear map. Just with the transcendental perturbation, you can basically see that the linear behavior survives in a quadrant. And when you look at this quadrant and you manipulate it appropriately, you see that this is contained in a F2 component, which is this peculiarity, or it has two peculiarities. First of all, that the limit functions go over the entire line at infinity, so they're really rank 1 limit functions. for this very specific class of maps. So in the small class, not in the large class of automorphism, like we had in Jupiter-Lilov and in Bracci-Boktalev example. And then what I think is interesting, before we move to the open questions, what I think is interesting about this example is that it's a different dynamical behavior than the examples found by Jupiter-Lilov and Boktalev-Bracci-Peters. So this kind of helps us understand this a new type of dynamical behavior that you can have on two components which converge to a rank one manifold, to a manifold of dimension one. And then just to complete the picture of what we know about escaping for two components, you can also construct escaping for two components whose limit functions are points on this line of infinity. Let me say, no, I think this is kind of okay. So the bottom line is we don't have a classification of escaping for two components. We are far away from this. Escaping for two components have not basically been studied before because people concentrated on polynomial automorphisms, for which they are well understood. If you move up to transcendental automorphisms of this special form, which are these transcendental phenomenon, so they have a lot of extra properties. They're not random automorphisms. You can construct examples of escaping for two components which are different from the attracting basis. And what is interesting is you can construct examples in which your limit manifolds are rank one. And of course, it would be nice to have a classification. There are many, many questions that one would like to answer. We need many graduate students. And well, instead of leaving the thank you slide, I will leave it on the slide with open question. And thank you so much for getting to the end of this technically difficult talk.
Are there questions?
Yes. This is sorry, wait. But I think this is more interesting.
No questions from the from there here. Okay.
So you showed before these data components and behavior. My question is, can you somehow exclude or an example of different types of convergence to respond in the sense that convergence might be tangential and tangential and also oscillate or
in one variable?
Yeah, one variable person. I had mentioned would be interesting, but it's very hard question. But in variable, one variable, the example you put is either convergence is tangential, so
it's a bit more delicate than this because I think it's true, but the conjugation to the half plane holds in a subset of the Baker domain. So maybe you are tangential in the subset, but there is more space in the Baker domain. It's not completely clear to me, at least. So yes, in the subset it looks tangential, but the normal form is really in the subset because as soon as you catch critical points, you cannot go back with your normal format. So I don't think this is true, but maybe the Baker domain could be larger. Maybe somebody knows that, but I'm not. Okay, thank you.
The next one is